Okay, I think it's about time. Okay, good morning, good afternoon, good evening, depends on where you are. I'm Tsung-Yi, the current Vice President of Technical Activity of the ICCAD CEDA. It's my honor to have Professor Elison Matioli from EPFL as the CEDA keynote speaker to talk about a very hot topic on compound power electronics. Before his excellent keynote talk, I would like to briefly introduce ICCAD CEDA for all of you. Okay, the CEDA is one of the 46 societies or technical councils of the ICCAE. It was established in 2005 to foster design automation and test of electronic circuits and systems. And CEDA enables technical information exchange and community services through publications, awards, conference, technical activities, etc. For publications, CEDA published the ICCAE transactions on CAD, ICCAE design and test of computers, ICCAE embedded system data, etc. For awards, CEDA offers the Field Kaufman Award, as known as the Nobel Prize in EDA, Richard Newton Technical Impact Award, Ernest Kuh Early Career Award, etc. For conference, CEDA sponsored more than 50 conference symposiums, including the 5 sister conferences, ICCAD, DEC, DATE, ASP DEC, and ES Week. For technical activity, CEDA hosts the CEDA Distinguished Lecture Program, chapter events among 16 chapters worldwide, 5 professional technical committees, young professional activities such as PhD forums, and so on. So please join CEDA today if you haven't done yet. It's free of charge. We very much welcome our friends to join CEDA activities and more importantly, be our CEDA volunteer. Okay, so now I would like to introduce our prestigious keynote speaker, Professor Elison Matioli. Professor Matioli is a professor in the Institute of Electrical Engineering at EPFL since 2015. He received a bachelor degree in applied physics and applied mathematics from Ecole Polytechnique in France, followed by a PhD degree from the materials department at the UC Santa Barbara in 2010. So after that, he was a postdoc in the EECS department at MIT until 2014. He has received the UCSB Outstanding Graduate Student Scientific Achievement Award for his PhD work, the 2013 ICCAE George Smith Award, the 2015 ERC Starting Grant Award, the 2016 SNF Assistant Professor Energy Grant Award, and the 2020 University Lattice Prize. Okay, so welcome, Professor Matioli. The time is all yours.
Thank you very much. Thank you very much for the introduction, and also the invitation to share our vision on the challenges and opportunities in gallium nitride power electronics. So power electronics is today the backbone of electrification of our society. It's basically becoming one of our basic needs of this 21st century. And power electronics is basically what enables us to have renewable energy sources, to electrify our transportation, and also to power up the data centers that actually give us all the data needs that we have in our modern society of today. So more specifically, power electronics is basically what makes the interface between all of these energy sources coming from all different types of energy into all of these different applications, different types of ways to consume electricity. The idea is that this kind of circuits are what makes the interface between these two sides. And the goal of power electronics is basically to have this interface as efficient and as compact as possible. And the motivation for this is that there are huge losses in power conversion. When you look at the energy flow from the generation to distribution, all the way to the consumption, we see that there are many different steps of power conversion along the way. So you change from AC to DC, different voltage levels, different current levels. And oftentimes these conversion steps are cascaded. So when you start cascading conversion steps that are not 100% efficient, the whole efficiency of the system drops very quickly. So it's estimated that about 20% of all the electricity consumed in the world is lost in this cascaded power conversion that we have. This basically exceeds the entire supply of solar and wind sources. So in itself, it becomes quite a huge source of energy. And even an increase of just 1% in efficiency in the power conversion could be a significant amount of energy that we can harvest from this loss. Another main motivation is to have more compact power converters. So if you look at the evolution of computational power from the 80s to today, we basically carry this extremely amazing computers in our pockets. But if you look, we didn't see the same kind of evolution in terms of power converters. So the power converters that we have today are about the same as they were in the past. And to understand limitations, we can open one of these power converters. So here what we see is very big discrete devices that are connected to this massive heat sinks, just a piece of metal there. We see this very large magnetic components, inductors and transformers. We see these large capacitors. So if we want to reduce the size of the circuits, first we need to improve the efficiency and reduce the size of the devices themselves. So today, those are discrete devices that are quite big. And the idea is to make them smaller and more efficient. The second one is to increase the switching frequency. So all of these energy storage elements, so transformers, inductors, capacitors, their size goes inversely proportional to the switching frequency. So if we can switch faster, we can reduce the size of these components. The third point is to enhance the thermal management. So we can basically eliminate all of these big metal pieces that we have inside the circuits. And for this, gallium nitride is truly an exceptional material. So when you compare gallium nitride to silicon carbide or silicon, we already see that these properties are much better in the sense that we can now hold, say, thousands of volts with a much, much smaller resistance compared to these other materials. Gallium nitride are lateral power device. So that means that because of their very intrinsic property, which is polarization fields, when you put together a material of aluminum gallium nitride together with gallium nitride, there is a layer of electrons that's created right at the interface. So this is a two-dimensional electron gas. So to make a transistor, you just put a source, drain, and gate in between, and then you can have a transistor where the current actually flows laterally. And the fact that we have this lateral device now enable us to integrate more devices side by side in the same chip. The third very important point of gallium nitride is that it's grown on large area silicon substrates. So it means that you can have large area low cost device on silicon substrates. This device now, these electrons, they have very large mobility, very large carrier density. So it also means that we can switch them at much higher frequencies. So we can reduce the size of those passive components. And we can start thinking about integrating not only the transistors, but also logics and everything inside the same chip, so we can eliminate some of this parasitic inductance when we connect the different components. So the challenge of the current devices is that even though gallium nitride offers a very good limit in terms of the material, when you look at the performance of current device, those are these red dots, we see that there's a huge difference between where we are today and where the material is capable of giving in terms of performance. So, so to reach this, we basically want to increase the breakdown voltage and reduce the on resistance. We want to do all of this while having normally off operation. For power electronics, normally off is extremely important. So then we can reach the limits of gallium nitride. A second point is, if we want to go towards integration, where power device can be combined together with logics, together with level shifters, together with gate drivers and everything, we have the problem of gallium nitride is the lack of p-type gallium nitride. So that means that CMOS is not really available to do logics as we do with silicon device. And the third problem is that if we integrate all of these different components in the same chip, then thermal management becomes a problem. How can we extract the heat that's generated in such a tiny chip? So in this talk, I would like to discuss some of these challenges and also offer maybe some possible solutions to address these challenges. So in the first part of the talk, I would like to present some pathway for efficient power electronic device, where the idea is to increase breakdown voltage and reduce on resistance. The second part, I'll cover the pathway towards integrated power chips. So what's blocking us from going there, where we are today, and what's the future perspective. And the third part, I'll discuss about thermal management. How can we extract heat out of this highly integrated power components now? So let's start with the first part, the efficient gallium nitride power electronics. So when you look at today's gallium nitride devices, the picture is a bit more complex than the one that I just showed. So this is a schematic of a more realistic device. The device is composed not only of the source, gate, and drain, but now we have several field plates. Those field plates help to manage the electric fields that we have when we are holding large voltages. The gate, we need to insert some technology to actually make it normally off. The main problem is that the two-dimensional electron gas naturally connects the source and drain sides. So to make normally off, we need to break the connection between the source side and the drain side. So there are ways to do that. Then in the wafer side, there is quite a lot of technology in growing gallium nitride from the silicon. Those are not the same kind of lattice constants. So there is a lot of strain balancing that needs to be done between the silicon and the gallium nitride. That layer we call the buffer layer. And also to dope that buffer layer in the right way so it can hold large voltages. And the final part is actually the barrier material, so aluminum gallium nitride and gallium nitride, to make the device a low resistance, high mobility, and breakdown voltage. So I'd like now to discuss the trade-offs that we have in gallium nitride technology. So the first trade-off is between on resistance and breakdown voltage. The whole point is that gallium nitride is a lateral device, and large voltages are actually held between the gate and the drain. So it's in this distance here. So typically speaking, you want to make this distance as large as possible so you can hold more voltage. But if you do that, the trade-off is that you increase the resistance of the device. As a matter of fact, the resistance goes the square of this distance. So as you increase the distance between gate to drain, we can see the resistance going up as the square of this distance, and we can see the increase in breakdown voltage. The increase in breakdown voltage actually happens until we reach a limit of this buffer layer. So there's a moment where the device increasing the distance between gate and drain doesn't help in terms of holding larger voltages. We're limited by this layer. So at the end, we can see in this plot of on resistance and breakdown voltage that there's not much we can do. If we increase the breakdown voltage, we increase together the resistance. So there's not much we can do to actually make this to go down to the level that gallium nitride is capable of. A second problem is how to achieve normally off operation. As I mentioned before, we want to break the connection between the two-dimensional electron gas on the source and drain sides. And there are many ways that have been proposed to do that. So for example, one way is to recess the gate, which means just by removing part of the barrier, we can break the connection between the two sides of the two deck. We can also break this connection by implanting negative ions on the barrier. So that depletes the electrons under here, so you can have the disconnection between the two sides. We can also include a p-type gallium nitride layer. So by doing that, we can basically lift the conduction and valence bands in a way that we can deplete the electrons in the two-dimensional electron gas just under the gate. And another approach that can be also found today is where we have a cascode structure. So it's basically, instead of making E mode or normally off gallium nitride device, we keep it normally on, and we connect that to a normally off silicon MOSFET. So the idea now is that you have two devices connected in the same package, and the normally off is basically taken care of by the silicon MOSFET. So the problem here is that, again, we have a trade-off between threshold voltage and current and resistance. So to make a very positive threshold voltage, you want to make this region of any one of these technologies, if it's recess, if it's the implantation, if it's GaN, as long as possible. But if you do that, then you also increase the on resistance. And this can be seen in this plots. You can see that any of the points in the literature, typically when you increase the threshold voltage, you reduce the current. When you increase the threshold voltage, you increase the resistance. So there's also a clear trade-off between these two, these three variables. So I would like to present here ways to deal with these trade-offs. And the idea is to use nanostructures for high voltage device. That may sound counterintuitive, but actually it works really well. It's very similar to FinFETs or tri-gates that we see in silicon devices. And the idea is very simple. So we take a portion of the gate and we make these tiny trenches etched on the gate. Then when we deposit a gate metal, we actually form a gate that goes around this fin. So we have now gates on the sides and on the top. So we call this structure a tri-gate. And this structure has been shown in the past to improve the control over the two die, because now we have gates all in the three sides of the fins. But what I believe to be the most important feature of this is the fact that we can design the threshold voltage. So here, if we change the width of these fins, as shown here, we can basically design the threshold voltage from what you have in a planar device all the way towards 0 and positive values. Another variable that we have is the filling factor. So it's basically the ratio of the unetched part to the etched part of these trenches. If you increase the filling factor, we can see that the on resistance can be reduced. So if you optimize these two variables, now we can have devices that have exactly the same on resistance as a planar device. Even though we are etching away material, we are removing electrons, we still have the same resistance. And another interesting is an increased breakdown voltage compared to a planar device. And the reason is that since we are reducing the threshold voltage in this tri-gate region, we're basically converting for free the rest of the gate into a field plate. So I'm going to discuss about this in a few slides. So the fact that we can now change the threshold voltage by reducing the size of the fins enables us to really push this towards positive values by actually having fins of a few tens of nanometers. If we go down to 15 nanometers, we can see that we start having a normally off behavior. And if we combine that to a large work function metal, for example, platinum instead of nickel, now we can get this value, the difference between the work functions in threshold voltage. So you can see a shift to the positive side in the threshold voltage. So it's a very nice normally off behavior. And here again, the important thing is that we can have the current and resistances that are very similar to those of D-mode device. So we are adding these things and we still have the exact same resistance and current of device that were planar in D-mode. And the reason is that now the conduction doesn't only happen through the two deck, but also it happens through the channels that we form on the sides of these things. So we have an MOS in accumulation mode, as you can see here from these two peaks. And this device, even though they are only 15 nanometers in size, they still hold 1.4 kilovolts. So that shows that nanowires can really be applied to high voltage operation. And here the tri-gates actually, they ease the trade-off between VTH and on resistance for basically any of the technologies that I showed before. For example, if you combine a P-GaN with tri-gate, now we can have a positive threshold voltage with a much shorter P-GaN length. And now since the tri-gate doesn't disturb the on resistance, we don't really degrade the on resistance, but we get a more positive threshold voltage. So this can be seen here. You can see that we can reach with the tri-gate PMOS the same threshold voltage as we have with a typical PMOS P-GaN device, but instead of using 1 micron P-GaN length, we only need 100 nanometers. So now we can get an E-mode device with a much smaller on resistance compared to a typical P-GaN device. And the same can be done with gate recess. So now if we include just a tiny recess of 150 nanometers, you can see that the recess by itself is not enough to have a normally off operation. We're still very close to zero. But when we add a tri-gate to this tiny recess, we see an extra shift of the threshold voltage. So now we can have a very nice normally off behavior. This device can hold 2 kilovolts, and we don't see a degradation in on resistance that we would see if we increase the P-GaN from 150 nanometers to 500 nanometers, as you can see here. So basically, this is enabling us to ease the trade-off between current and VTH. So now we can start getting high currents with a high positive VTH, together with a low on resistance, so in a high VTH, together in the same device with a high breakdown voltage. It's possible to have these elements separately achieved in devices, but it's very difficult to have them all simultaneously achieved in the same device. So tri-gate here enables us to have this kind of eased trade-off. So now I'd like to discuss the use of these technologies for high voltage operation. And one of the problems of GaN is that it's a lateral device, and the electric field is also highly inhomogeneous in this device. So if you have your device, you turn off the gate, you're holding a large voltage in the drain, the electric field typically peaks at the edge of the gate. That's where the device breaks. So to fix this, what we do is we add a field plate. Field plate is basically another transistor with a thicker oxide. so a more negative threshold voltage. So by doing this, we actually split this peak into two. So we have two peaks now, higher breakdown voltage. And you can keep going. You can add another field plate. You have three peaks. And the ultimate configuration of this would be one where the oxide thickness could be changed basically smoothly and in an angle. So basically, threshold voltage now is being changed just progressively in this area. So the electric field can be very homogeneous under this gate region. So this is a well-known concept. It's called the slanted field plate. You can see here it works really well. The only problem is that it's very difficult to make this angled oxides in typical clean room environment. And also you don't have a lot of flexibility. You can't really choose the angle that you'd like to have. It's very difficult to make this. But here we basically borrowed this idea and came up with a new one that's called the slanted tri-gate. The idea is very similar. So if we include a tri-gate region on a planar device, we're basically creating a region of a smaller threshold voltage in the tri-gate. So effectively, we have two transistors connected together. So we split this peak into two. If we add another tri-gate with a larger width, we can now have three regions of different threshold voltages. So we have three peaks. And again, we can do this in the same way. We can just angle the sidewall. So we can have a continuous change in the threshold voltage. And now the electric field is homogeneously held under this region. The whole point here is that this can be done in a single lithographic step. You can basically change and select the angle that you'd like to have. It's a very, very easy process to do. So we made this device. You can see a planar, a straight tri-gate device, and a slanted tri-gate device. So you can see the angle of these features going, from 350 nanometers to 700 nanometers. And when you look at the breakdown, the planar device was breaking at 900 volts. Tri-gate device was breaking at 1100 volts. And the slanted tri-gate device was breaking at 1400 volts. These are all devices made side by side. The only thing we're doing is changing and adding these tiny structures in one single step in the process, and we gain basically 500 volts in breakdown voltage. Or another way of looking at it is that we reached this buffer limit of the GaN on silicon with a 5 micron less size. So basically 2/3 of the size that we had before. So this is an effective way to reduce the R1 times area of the device or to enhance the breakdown voltage. So effectively, what we're doing is just moving towards this high voltage side of this plot without really degrading the on resistance. That enables us to push the breakdown voltage of the device. So this is quite effective to have high voltages. The question now is, how can we reduce the on resistance? We would like to actually go much closer to the limits of the gallium nitride. So for this, we propose the concept of multi-channels. And the idea is basically what we're trying to solve is the trade-off between carrier density and mobility. So if you take a typical barrier, so aluminum gallium nitride, there's not much you can do in terms of changing NS. So if you increase the carrier density, you basically reduce the mobility. And if you try to reduce the carrier density to enhance the mobility, you have to reduce the carrier density in a way that basically the sheet resistance is more or less fixed. So in this case, 400 ohms square. You could change the material. Instead of aluminum gallium nitride, you have indium aluminum nitride or aluminum nitride. You can gain a little bit, but not that much. And actually, you still see the trade-off between carrier density and mobility. So now to break this trade-off, instead of using a single conductive channel, we basically made we stacked several two-dimensional electron gases in the same wafer. So the idea is that now we have several conductive channels together. And actually the whole technology involves the multi-channel tri-gate, so we can control all of these channels from the sides of this gate structure. And we terminate this with this slanted tri-gate termination that I just showed to you. All right, so when we made this, this device, what we could see is that we can completely break the trade-off between NS and mobility. So while before we were at 400 ohms square, now we have a 5 times less, so 80 ohms square. So basically we achieve a high NS with a high electromobility. But the problem is that having this extremely high conductivity wafers is not really useful if we cannot control them. And that's the case if you apply a planar gate. So if we put a planar gate on top of these multiple channels, the problem is the gate is not able to switch off the embedded channels. So the device is always on, even though we apply minus 40 volts to the gate, the device is still on, and the gate actually breaks and the device is still on. So it's not a very useful device. But if instead we use a tri-gate structure, the idea is now that we can switch off all of the channels from the sides, we can see a very nice on-off ratio. So the device can be controlled very nicely. As a matter of fact, we can now change the width of these things, and we can change the threshold voltage of the device. You can see that if we go in towards a 40 nanometer thin width, the threshold voltage actually moves towards 0. And more interesting is that when we have a wide fin, we can actually see all the multiple channels being switched off at different voltages. When we have a 40 nanometer channel, we see that all of these peaks in transconductance become a single one. So it means that the device behaves as a single transistor. So now we made a power device. The gate has 15 nanometer fins, as I showed before, together with the high work function gate metal. And this only takes a small part of the device. So now we can see very nice and positive threshold voltage and very small on resistance, both for the E mode and D mode. So you can see the device has more than 2 times lower on resistance than any device in the literature. And another interesting point is that we see that the dynamic degradation that's quite well known for a single channel device actually become much less when you have a multiple channel device, because now we have a lot more electrons for the same trap density that we had before. So the ratio is favorable in our side. So finally, we would like to hold large voltages. And the problem is that if you take a single channel, in our case, we're holding 1.4 kilovolts. When we make the sheet resistance smaller and smaller, so the wafer more conductive, we see that the breakdown voltage decreases as we move forward. So we basically have, to the very highly conductive wafer, we only have about 40 volts of breakdown voltage. It's not a really useful power device. And so to basically solve this, we now, if we include a tri-gate device, a tri-gate feature, or a slanted tri-gate feature, we can see that the breakdown voltage is basically just being increased to from 40 volts to about 600 volts to about 1,200 volts. So we basically gained a factor of 25 times in breakdown voltage by introducing this slanted tri-gate region. And after this, we optimized the device and we could reach a very high breakdown voltage, 1.3 kilovolts, while still having a very small leakage below 20 nanoamps per millimeter. So even though we have a very highly conductive wafer. So this shows that actually the gate can control the leakage to a very low level, even though we're applying a high voltage to the drain. So at the end, this device showed very good performance. So much smaller on resistance compared to basically any device in the literature of the same voltage range. And now we could significantly reduce the on resistance resistance while keeping a high breakdown voltage. And basically, for the first time, we could cross this limit of the silicon carbide region. And this was only achieved with 4 channels. So nothing really prevents us from adding more channels and getting to the gallium nitride limit. So we believe that this is a promising pathway for more efficient power electronic device in the future. So now let's discuss the second part, which is going towards an integrated power chip. So if we look again at our basic schematic, here, when you look at the dynamic behavior, actually the properties that are important are related to the input capacitance, the output capacitance, so basically this region here. So every time we hold large voltages, we're basically charging this capacitor. And if you try to switch really fast, you need to charge and discharge this capacitance. And we have some degradation in the own resistance in gallium nitride when you try to switch really fast. So let's discuss this point. So basically, if you take a device, we can break down the losses into 3 components, especially for high switching frequencies. So we have the gate losses, everything that's related to the input part of the device. We have the output capacitance, things that are related to the output of the device. And we have the conduction losses, both the static one and the dynamic one. So if you look at gallium nitride device, you go to the data sheets, you see that GaN, for the same kind of voltage and current, it offers a much smaller gate charge compared to silicon carbide. So it's a great thing. But then once we measure those devices, one thing we realize is that gallium nitride is not a single technology. It's actually, there are several different ways of making gallium nitride device. And depending on the technology, we notice that the input capacitance versus voltage may vary completely from one device to the other. If you take a PGAN gate injection transistor, you realize that the gate actually works as a diode. So you inject current, so you have a much larger input capacitance. And basically the integration of this will determine how much losses we have when you start switching this device. So here you can see that if we want to go to the megahertz range, we need to start looking at the effect of CISS, so input capacitance, on the total losses. And you can see that even though GaN should have a much lower loss compared to silicon carbide, depending on the technology, this might not be completely the case. So we need to be careful what we are selecting, and not all gallium nitride is gallium nitride as the theoretical definition of it. The second point here is the output capacitance losses. So this is all related to charging this capacitor when we're holding large voltages. So you can basically switch those devices in 2 ways. It's hard switching. Every time that you go from off to on, you're throwing away all the charges that we have in this capacitor, or soft switching, which is basically you turn off and turn on the device in a way that those charges are not completely dissipated. The idea is that in theory, if you soft switch a device, you shouldn't see much losses from output capacitance. But in practice, what we see is when you do a sweep of the charge and voltage plots, you can see that some of the devices behave in a very special way. They have this hysteresis between the 2 curves. So it means that the charge and discharge cycles are not the same. So every switching event, we have the area between these 2 curves being dissipated and thrown away. So if you start switching at megahertz range, this might start being a problem. So you can see again that some gallium nitride devices don't have these problems, but some do, and the same for silicon carbide. Some don't, some do, it's smaller, but it's still there. So now you can see that there is a difference in the energy dissipated from some types of gallium nitride device, for example, the PGAN gate, to other type of device that can be more than an order of magnitude higher energy dissipated, even though you're selecting the gallium nitride device with the same kind of specs. And the interesting part is that we can actually model this output capacitance with a small signal model. We can add loss terms like this RS and RP effective resistors, and we can treat this the same way as we do with capacitors. So we look at this in terms of quality factor. So we look at the output capacitance in terms of its quality factor. So if we measure this and we model with small signal, we can see, we can basically extract all of these components. And if we select devices that have very similar output capacitance from silicon carbide or silicon, they might have completely different series resistance as we show here. This is a complex number. It's not exactly just the leakage, but it represents losses in general. And the interesting thing is that if now we take a device of this blue curve with a lower RS compared to this orange one, and you just switch on and off the output capacitance, we're not doing anything else, you can see the effect in terms of temperature if you switch at high frequencies compared to this other device. So it means that we need to be careful about these extra losses that we have in output capacitance as well, especially if you're going to megahertz applications. And finally, it's the conduction loss, the dynamic degradation of RON. So we can measure the static RON, but actually when you start switching the device, it's well known that gallium nitride may have some dynamic RON degradation. So you can see again in all of our types of devices, even though all of the data sheets and these are all commercial devices, they all say that there is no problems with them. But when we measure, we see that some of them have acceptable values up to 10% degradation, but some of them may have up to 60% degradation in dynamic on resistance. So if you start switching this device, their effective resistance is actually 60 times larger than what you expect. So now we have a whole breakdown losses of the different types of devices. So you can see the output losses, power losses, gate power losses, and conduction losses for all types of gallium nitride and silicon carbide transistors versus frequency. So if we are aiming to switch in the megahertz range, then we can see that typically gallium nitride can offer a much better performance compared to silicon carbide, but it's not every device that behaves the same way. So we need to be careful with the device that actually can switch at the megahertz range. So the second part that I would like to discuss is the monolithic integration of devices and gate drivers. So the whole idea here is that if we put all of this, not only the power devices, but also the gate drivers and logics and everything in the same chip, we basically can eliminate the effect of this parasitic inductance. So we can switch at megahertz without really generating any ringing inside the device. So the problem is that today gallium nitride has no good p-GaN channel. So we cannot really make CMOS logics on GaN. So basically what we have to do is go back 40 years and look at the NMOS kind of logics as we used to have for silicon in the early days. So the whole idea is that to have a normally off gallium nitride transistor connected to some sort of either static load or a dynamic load made with a E-mode gallium nitride or a D-mode gallium nitride. So the idea is that if you make this kind of device, you can start making logic. So for example, here's an inverter. It's a very nice behavior. Of course, because it's not CMOS, to reach a low voltage here, we basically need to design the relative size of the top transistor and the bottom one. But the advantage of GaN is that these inverters now can operate at really high temperatures. So you see 300 Celsius and the inverter still operates very nicely. And we are actually in a very, very special time. So today we can purchase already, there are commercially available monolithically integrated device and gate drivers in a single chip. So basically you can see not only you have the power device on the same chip, but also logics, level shifting, gate driving, and everything together. So you can purchase this. So for relatively low voltages, you have EPC selling those devices. You have for higher voltages, Navitas, for example. And here you can see the advantage is that if you use discrete gallium nitride device, you can see some ringing happening, which doesn't really happen in the GaN power IC. So it enables us really to increase the switching frequency. So our question was, how fast can this tri-gate device really go? And to tackle this, we basically made a tri-gate diode. So the idea is pretty much the same, except that we make a Schottky contact directly to the fins. So there's no oxide in between. And we have this region where we have a tri-gate MOS just connected next to it. So the whole idea is that if you apply a negative bias, this region depletes the channels, and then the leakage current can be significantly smaller. And that's what we observe. So if you go to a planar device, we see that the tri-gate device that we call now tri-anode, they have a much smaller leakage, and they have a much smaller gate capacitance. And well, capacitance in this case. The whole idea is that we are removing electrons under this region. So that's what makes the capacitance to be much smaller than what we typically have in a planar device. So if you have a smaller capacitance or smaller charges, at the end, we can switch much faster, and you can see a much reduced reverse recovery in this device. So here's our tri-anode device compared to a planar GaN device. And so we can gain a huge amount in terms of the figure of merit of R1 times Q. So R1 times charge, reverse recovery. So if you include the tri-anode by reducing the width of the sphinx, we see how much we can gain in terms of the figure of merit. And of course, now we can switch, we can operate this device and see that they offer a much smaller reverse recovery charge compared to silicon carbide or to silicon, the fast recovery diodes. So you can see that this reverse recovery time is much smaller than what you have in these other devices, which actually corresponds to a much smaller power loss at every switching event. So as a consequence now, we can switch at higher frequencies with a much lower losses. So for example, silicon device, we reach 1 watt of losses if we switch at 100 kilohertz, whereas for gallium nitride, we can switch beyond 5 megahertz and still be really far from this 1 watt limit. So it shows that, again, we gain also in the turn on voltage times QRR figure of merit compared to the silicon and silicon carbide. So the whole point is that now this opens a pathway for new topologies where we can actually take advantage of this extremely high switching frequency that were not possible before. So here, just to tackle this, we made an integrated diode voltage multiplier. So the idea is to put a lot of diodes together. Those are 1.2 kilovolt diodes with the tri-anode technology, all in the same chip. And we make a diode multiplier. So depending on the number of stages, we multiply the voltage by 4, by 6, or by 8 times. And you can see the advantage. We're basically replacing all of those discrete diodes by a single integrated chip. So we see much less ringing. We see also that, again, we can operate in the megahertz range with much smaller losses than you get with the silicon diode. The whole problem is that now we are dissipating this loss in a much smaller surface than what we had before. So even though the losses are smaller, but the power density is quite high. So you can see here temperatures reaching very close to 100 Celsius. And that's actually a common problem for any integrated power chip. Electronics will be solved, and the question will be, how can we manage heat in these highly integrated devices? And here I go to the third topic of this talk, which is managing ultra high power density. So for this, we basically are looking into microfluidic cooling. So the whole idea is to make microfluidic channels on silicon and flow coolants inside so we can extract heat. And we have three different levels. So we have one level, which is the indirect approach. So the idea is that we make a piece of silicon, a cold plate, we attach that with the thermal interface material to a packaged device. Then we flow liquid. This can cool down to heat fluxes of 100 watts per centimeter square. The second level is that we actually take advantage of the fact that gallium nitride is already on silicon. So we can create the channels on the back side of the gallium nitride chip. We flow liquids inside, and now we can get much closer to the hotspot. So in this direct approach, we can cool down 500 watts per centimeter square. And the ultimate approach would be what we call the co-design. It's basically one where we design the electronics and the cooling together. So we can now make these microfluidic channels in direct contact with the hotspot, and we can significantly reduce the thermal resistances that we see in these other two cases. And now we can cool down heat fluxes up to 2 kilowatts per centimeter square, extremely large heat fluxes. So let me show this approach here in this talk. So the idea is that at the moment that we're making our transistors, we make these incisions on the gallium nitride that reaches all the way to the silicon substrate. Then we can create these pockets, so these microfluidic channels. And from the back, we make a network of distribution liquid. So the idea is that we distribute the liquid from the back. It goes into each one of these micro channels, and it travels a very short distance, so the pressure drop can be reduced, and it absorbs the heat, and it goes away. So you can see here the picture of the top of the device and the back of the device. You can see the microfluidic channels here. And when you look at the thermal resistances of between these three different approaches, you can see the massive reduction that you can have when you go from the indirect to this co-designed approach. So in the indirect approach, we had the junction to case, thermal interface material, convective and conductive terms, which basically got completely eliminated by putting the microfluidic channels in close proximity with the gallium nitride. So by doing that, we can now achieve very high coefficient of performance, which is basically the efficiency of the cooling, while extracting heat fluxes of 2 kilowatts per centimeter square. Of course, we optimized everything. We optimized the micro channel itself. We optimized the distribution network that we made to achieve this high performance. And here I'd like to show how this works. So we take our chip. If you flip it, you actually see on the silicon part this distribution network. So the fluid goes in. It's distributed into each one of the microchannels. It extracts the heat from the gallium nitride layer, and it leaves the chip. That's it. The whole idea is that the length that the liquid travels inside the microchannels have to be minimized to minimize the pressure drop. So here's an example. We have a device. There's no liquid flowing. The peak temperature is at about 100 Celsius. And then we start flowing liquid. You can see that immediately it goes to room temperature. It's a very, very way to extract heat. And of course, if we stop flowing liquid, you see the temperature just rises again. But it's not only that we're extracting heat, it's also that the current when the device is cool is actually much higher than when the device is hot. Of course, we don't have self-heating degradation. So effectively, the device becomes more efficient with less resistance when it's being thermally managed. So it's a win-win situation here. So finally, to demonstrate the power of this kind of approaches, we integrated 4 of those 1.2 kilovolt diodes, trianode, to make a full bridge rectifier. We integrated that together with our cooling technology in the same chip. So it became a fully integrated power IC. You can see here the picture. And then to operate this, we basically had to make a new PCB. The top layer of the PCB distributes the electronics. The middle layer of the PCB distributes the liquid. So we have now everything that looks like a USB stick, but actually can handle 5 times more power than a regular laptop charger. So now we have a converter that actually operates with a much lower temperature rise. We can reach a higher efficiency and still operate very close to room temperature, while if we were operating with air cooling, the device would be at 250 Celsius at this point. So finally, just to really show the full potential of this, we integrated our cooling technology, the microfluidic cooling, on a commercial integrated commercially integrated half bridge with gate drivers, passives, logics, and everything inside. So we just took one of those commercially available chips, we post-processed our cooling technology, and we made an entire buck converter in a tiny little form factor. So here the buck converter converts from 48 volts to 24 volts. You can see here where the liquid goes in and goes out. Basically, we cool down everything, passives and the active components. So here you can see the trade-off between pressure drop and thermal resistances with flow rate. So if you increase the flow rate, of course, we reduce the thermal resistance, but we increase the pressure. So we just selected the flow rate where both of these terms are small. And another interesting trade-off is in terms of the switching losses. So if you increase the switching frequency above 1 megahertz, then the switching losses from the power devices dominate the efficiency of the entire converter. And if the switching frequencies are too low, then the inductor losses dominate the losses in the entire converter. So basically, we picked the best value here that has a good trade-off between these two, which was 1 megahertz, which is a very high switching frequency. And now this integrated power chip could operate with 5 times higher power than it was operating with air cooling. So we basically reached 450 watts in this tiny little thing with an efficiency of over 95%, while we're still operating at much lower temperature than when the device was with air cooling at 4 times less output power. So this shows that now we can have 450 watts in this tiny little chip. So it's 78 kilowatts per liter that we can reach with a very high efficiency. So it shows really the power of this integration altogether. And to conclude this talk, I basically would like to share the opportunities that I foresee with in this field. I do believe that the future of power electronics is integration. I don't think that for this power level we're going to see many discrete devices in the future. I think they're all going to be integrated I have here in terms of device modeling, in terms of EDA, is we need to basically create ways to model several of these devices operating together in the same chip. So we're going to have low voltage devices with high voltages together side by side. And today we have a lack of proper compact modeling tools already to represent the correct behavior of gallium nitride devices. So you can see that the behavior is quite specific, but so there's already a lack of this proper modeling tools for gallium nitride itself. And I do believe that we need to start looking into these novel technologies that are coming, how to include them into these models. And I believe that there is an opportunity for also cooling to be designed as an integral part of the device. So at the same time that we design the electronics, the cooling will be designed based on the heat map of the device. And finally, what I think is that today we are basically doing the optimization of these components in a blind way. So we design separate transistors, we design the cooling and everything. But I believe that a computer-aided design will enable us to automatically optimize the entire circuit. So what is the effect of changing some parameters on other parameters of the device? So I believe that there is a huge opportunity in this field for EDA tools. And I would like to thank you all for my presentation and thank my entire group and the source of funding that we have. So thank you very much.
Okay, thank you, Elison, for the wonderful talk. Yeah, your talk is very inspiring. So actually, your talk already passed for 5 minutes. So some audience, I think they already left for another section. Okay.
Oh, sorry.
No problem. Because your talk is very inspiring. So I would like to, yeah. So I don't want to remind you. Okay, it's good. Yeah.
I appreciate it. Thank you.
Yeah. So now we are open for questions for the audience. Yeah, you can type your message or you can raise your hand. Oh, okay, it's one. Yeah, right. I think maybe you can. Yeah,
there's
Professor
one.
Pong. Yeah.
Hello. This is Yare Pong from University of Arkansas. First thing, very nice talk and very interesting. So here at University of Arkansas, that we probably is more looking at silicon carbide instead of gallium nitride at this moment. But we do feel that the wideband gap transistor technology and the integration of high power and low power together through heterogeneous integration is the kind of the future of the computing. So I do have a few questions to you, especially given the scope of this conference is on the EDA and the CAD tools. So the first thing I want to mention is perhaps you mentioned about the need, for example, to co-design the the thermal cooling system along with the device and circuit together, right? So I think this calls a very interesting topic. Not only just what you mentioned about, let's say, considering the device behavior together with the cooling of the temperature, for example, the resistance, but also if you think about, let's say, the placement and routing of the devices and inside a converter, and how to co-design the cooling system along with the passive components, with the gate driver, with the logic components together, right? So that actually gives a lot of opportunities on many different scopes of, and we need to bring designers and engineers have a background and knowledge from all perspective, low power device, and even the system designers together. So how do you think that the industry should work together to bring those different background, different knowledges together, especially traditionally these different high level and low voltage societies are kind of separated in terms of the knowledge and the training and the students. So how do we work together from that perspective? So that's my first question. And my second question is to the CAD society. If you look at how the VSI CAD is growing in the 1970s, 80s, the silicon, the foundry design the design house and the CAD community, they kind of need to work together to bring these new technologies together to kind of boost and to be able to utilize these new technologies. Just as some of the devices you mentioned today, that they are very promising, but if we cannot integrate them easily to integrate circuit or even small computer system, then it is still very hard for the industry and the entire engineering community to take advantage of those. So what do you think for from a CAD tool or EDA perspective, what are the needs and what are the future directions that we can pursue since that the power electronics CAD tools are still in its infancy, right? So how do we be able to truly utilize these advancements in the power electronics?
Yeah, so thank you very much. Very good points. I completely agree. What I believe, as you mentioned, I completely agree, is that we are in a very exciting time in power electronics. So basically everything is in its infancy. And I believe that gallium nitride, especially more interesting / challenging, just because it's still less mature than the silicon carbide, but more importantly, because the type of devices are different. The lateral architecture brings a lot of challenges that actually silicon carbide doesn't really have. So so this is the first point that I believe that the EDA community would make a huge impact, would be in basically being able to model correctly the behavior of gallium nitride device. What is done today is that you take typical silicon models and you try to estimate the effective parameters that would be used for gallium nitride. Unfortunately, it doesn't always work because the physics is not the same. So that's what I try to show with this output capacitance measurements, because it's not a single capacitor as you would see in other devices. Actually, it's quite a highly dynamic component that you have there. So I think the first thing is to be able to work on this device and not try to adapt them to the models that they have for silicon. And the second point that I think is quite important, and I believe that this is a very good step forward that ICCAD did, in bringing people from different fields to start this conversation. So I'm very happy to be here, because I also, from my side, I would love to have a better interaction with the EDA community to actually put in place all of these components together. One final point is that even the technologies in GaN today, they are not well defined in the sense when you compare to the different vendors. So everyone has its own technology for now. So we are still in that phase where we're looking to see which one is gonna prevail. So in a way, this is challenging, but it also opens a lot of opportunities to be at the right time and right moment to start implementing these things.
Right. Thank you so much. I think you made a very good point. I think right now the power electronics, the EDA society is more like in the 1980s, where we still have so much opportunities out there, and we're still looking at different technologies. But eventually that the society will kind of gradually settle down on a few more promising technologies. Gallium nitride is definitely one of them. So how do you think that your research, especially on the device modeling and the fabrication of the device, will be able to help the EDA society to adopt some of the some of the low voltage modeling techniques and design capabilities, and to kind of reuse and customize them for high power voltage, so that the industry will have a smoother transition and be able to gradually appreciate the invention of the high power techniques?
Yeah. So what we try to do is, in some of our own publications, is basically raise this points, just try to give our perspective on how things should be described. Even in a data sheet, a lot of the ways that we describe things are very reminiscent from the silicon world, and there are different ways that we could even present the information. But I do believe that the best way would be in a closer collaboration between the EDA community and power electronics, because then we can really try to together discuss on on the right way to do this. So I would love to find opportunities, to bring together more these two communities. That I believe that'd be the most promising way to move forward.
Thank you so much. Thank you.
Thank you.
Okay.
Thank you very much.
Thank you. We really run out of time. Again, I think the Professor Peng asked a very interesting question. I think his question I also would like to know. So I did not stop the session, but now we really run out of the time. And yeah, so once again, I would like to thank Professor Matioli for this wonderful talk. Okay, so I think we already recorded the video. We will soon we will put your video on the CEDA presentation library. Yeah, for those audience that they need to escape to another section. Okay, thank you. I think right now we also have some audience here. I think those audiences still be here. I think they are really like your talk. Probably they want to ask you some question offline, because I think we will not go to the gather time. Okay, I think we will stay here for maybe 5 minutes, maybe. Okay.
Sure. Yeah, I can stay a bit longer. It's not a problem.
Okay. Thank you.
Thank you very much. Thank you all for being in. Thank you.
Okay. I think we can start the recording now. Okay. Yeah. So I saw. Okay, maybe if someone have question, I think they can ask you now. Yeah, because I think we are not go to the gather time is a different interface. I'm not sure if you ever been there before. Use the gather time. Okay. I actually have one question. Yeah, one question. I think in July there's a research group from HKUST. They published this Gallium Nitride CMOS logic. Yeah, I'm not sure if you ever see this paper.
Yeah, I'm aware.
Do you think that that's a good way for large scale integration? No,
so I think this is another one of the topics that we don't know the right answer yet. And the main problem is that we don't have CMOS. So we need to come up with new ways of doing it. And most of the ways is based on NMOS. So basically you go back to the 80s to what what silicon was doing. And we're doing that on gallium nitride. So I think they do the NMOS. We also demonstrated like a lot of people are working on this. The whole question is, if we can demonstrate CMOS in the future, then it's going to take over. But before we reach to that point, I think all of these techniques will be very valuable.
Sorry, so I just want to cut in a little bit. So I do believe that in the long run, that I think CMOS for power electronics definitely will be very promising. But before we reach that, our solution at University of Arkansas, we try to use the heterogeneous packaging solutions. So to integrate, instead of the silicon gate driver, the logic, and power devices through advanced packaging, power packaging process. So just like you mentioned, let's say if we can integrate a gallium nitride device along with logic, along with gate driver together in a smaller substrate and together with embedded heat cooling, and even we can integrate it with the bus bar or the converter level design, then it's still that we are going to see very good efficiency benefits, the volume power density benefits through that, right? So what do you think that if we can, the opportunities and the research needed, if let's say we can integrate them on the package level instead of into monolithic chip with a power device. So if we can do that through packaging level, and what are the tools, maybe models needed, what are the design optimization algorithms, perhaps we will be able to boost those kind of opportunities there. So how do you?
Yeah. So I think the main point on this packaging level integration is also very good. It's, you know, even in the packaging, there is a lot that can be done. The whole question here is, what switching frequency are you aiming for? Mm-hmm. If you are aiming for the megahertz range, this might be a problem. Just the interconnection between the different chips might actually be enough that you start having some pretty huge ringing between the different components. But if you are switching at 100 kilohertz, this might be fine, might be completely acceptable. So at the end, I think that it's all a matter of what range of frequency and also voltage you're designing your chip for, you know.
Right. So we're trying to push to the megahertz range through maybe 3D packaging, so that we can potentially integrate multiple layers of device together before we actually can reach to a monolithic kind of integration in the future. But I think what you have shown here is a very promising way for us to consider, for example, have the embedded cooling so that we can control the heat dissipation and also be able to integrate different silicon components together. And I do think that even applying those for, let's say, the next generation data center, or even the high power density computing device with the embedded the power converters and power management together, I think that's a very good direction that the industry may trying to pursue.
So I can tell you one thing. After we had this this work published, basically most of the interest that we got were from data centers. So that's actually where the problem is huge. Right. So that's basically the direction that we are also considering, more than considering, because it is a big problem. Right. But if you think of for example, in terms of packaging, at the end of the day, I mean, this is a very rudimentary packaging that could be much more improved. You know, to have all the different devices, even if you integrate them in a 3D integration that you just mentioned, it's completely possible to have basically every component being cooled down with you know, using basically the same structure, but you can basically design the microfluidic channels according to the heat flux of each one of the components. So you cannot do that with a heat sink. Heat sink is just the same piece of metal. You cannot even get too close to the components. But here, depending on the dimensions, and that's where I believe that the EDA community can have a huge impact, because imagine that you can select the type of cooling according to, you know, the heat flux of that particular region of your chip.
Right.
And you just put that block of a given dimension, and actually you can flow the same kind of liquid, but you can extract much more heat flux on one region than in the other. So basically the gradient of temperature is constant if you design well your cooling. So there is a huge opportunity in that as well.
Yeah. Thank you so much. Yeah. So that's definitely
Yeah, I think Elison, I think how you mentioned this dedicated place for cooling. I think there are already a few papers using digital microfluidic. I think maybe 5 or 10 years back. But I know it's not easy to integrate to the current packaging technology. But there are indeed some, they can precisely control which location to do the cooling, not just use the channel. Yeah,
it's true. I'm not. I completely. I'm very aware of the past works. It's a very long field. I guess the what we did here that's quite different is the way that we basically co-design electronics and cooling. So now the microfluidic channel is under the hotspot of a transistor.
Yeah.
And before it was quite separate fields. So you do your chip and then you do the channels on the back. But here it's very together. So, and we can fabricate that together. We can even model that together.
Okay.
You know?
Yeah, I know. Yeah.
Yeah.
Okay. Okay. Thank you, Elison. Yeah.
Thank you very much.
Easier for us to ask the question here. So then we don't need to go to the gate time. Okay.
Exactly. That's
okay.
That's easy.
Okay, thank you, Elison, and thank you, Professor Peng. And yeah, I think there's still someone inside.